So in this video, we're going to be looking at methods for multiplication and division. Most of these methods revolve around some sort of grid. Now this grid method is used throughout the maths course, so not just in S1 but in S2, in S3 and S4 and even up to higher maths, where we use it for algebraic purposes. So part of our S1 maths curriculum is about looking at concepts and skills, building up people's confidence and familiarity with a certain approach, and then using that same approach for different purposes, whether it's number work or algebra work. So the grid method is very, very useful for that. So we're going to look at, first of all, multiplying by 10 and 100. So that's a little recap of the previous video. Multiplying by a single digit. Multiplying by 2 or more digits. Then working backwards in a way, and dividing by 2 or more digits, so commonly known or referred to as long division. And then we'll look at a couple applications of the use of a grid for multiplying and dividing. So let's have a quick recap of multiplying by 10 and 100. In the previous video, we looked at these exploding dots and this concept of we cannot have 10 dots in one section of the machine or of the table. So when we have 10 dots, those effectively explode and create one dot in the column to the left. So we have that sliding to the left. It doesn't matter where that is positioned in the grid. If we have 10 dots, that explodes and it becomes one dot in the column immediately to the left. That's then carried onto calculations like this one, 21.59 times 10. So we can think about our place values, the holders, the columns. There's my 21.59. Multiplying by 10 is sliding to the left. We don't talk about the decimal point moving at all. That's in a fixed position amongst the place value headings of hundreds, tens and units, for example. 34.5 multiplied by 10, one slide to the left. That's each column exploding into the next. In this case, we wouldn't write the final answer with the decimal point there, and we would just write 345. So it's the practicalities and sometimes the nuances of these questions that we 19 times 10, one slide to the left. The units position always needs to have a digit, of course. So that's the typical example where it looks like what we're doing is we're just adding a zero. And again, we don't talk about that when multiplying by 10 and 100. We don't talk about taking off a zero. When we're dividing by 10 and 100, we're talking about these sliding to the left. And in this case, the units position needs to be completed with a zero. 8.2 times 100. So 8.2 times 100 is the same as times 10 times 10 again. So that's 2 slides. And again, the units position needs filled with the zero. So our final answer is 820. 3.5 times 20. So 3.5 times 20, we multiply by 10 to make 35, and then we times that by 2 to make 70. So we can break down the 20 into 2 times 10. Timesing by 10, sliding to the left, and then timesing the 35 by 2 to make 70. That's a very quick recap of the previous video where we looked at multiplying and dividing by 10 and 100, and also multiples of 10 and 100. Let's have a look now at multiplying by a single digit. And we're going back to basics here. We have these Dean's blocks, or the base 10 blocks. We have a blue 100 square, 10 by 10, a green 10 rod, so there's 10 units in the green rod, and then we have the yellow cube, which is representing 1 unit. So if we took a calculation like this, 3 times 24, well, we could use manipulatives to illustrate this. So what we've got is 3 rows of 24. So there's 2 10 rods, 2 greens, and 4 units. 3 rows of 24 could be represented, or would be represented, like that. And even from this visual, you can see that we have 2 distinct sections. We have the green section and we have the yellow section. And that, in essence, is part of how we form our grid. To get the total, we could add it up in the green and the yellow sections. Seems fairly straightforward in some ways and sensible to add up the green and the yellow. So we've got 60 and 12, which makes 72. So 3 times 24 is 72. Traditionally, we might use a sort of a column layout for our working. 3 times 4 would be 12, and 3 times 2 would be 6. Add the 1, making the 7 and the 72. So you can see, having colour-coded it now, where the 12's coming from, the yellow part. The 7 has come from the fact, of course, that we had 60 and we added one group of 10 from the yellows. We're talking here about making use of a grid and starting to make use of a grid for multiplication. So to do that, this is how we would lay it out. And effectively, that's representing the Dean's blocks. We have the 3 rows along the left-hand side here. We have the 3 rows, and then we have the 20 and the 4, and we've split up effectively the 10s and the units, or the green and the yellow. So 3 times 20 would make 60, 3 times 4 would make 12, and the total of this rectangular area is 72. So we get the same answer. So the grid itself is a numerical illustration of the Dean's blocks on the left-hand side of the screen. So 6 times 27 using the grid, we would lay it out like that. 6 rows of 20 and 7, 10s and units. 6 times 20 is 120. 6 times 7 is 42. And the total is 162. So 6 times 27 is 162. So why don't you pause the video now and give this question a go. So in terms of the grid, we have 4 rows of 50 and 6. 4 times 50 is 200. 4 times 6 is 24. The total of the interior numbers in the grid, 224, 224. So 4 times 56 is 224. So that's a very quick illustration of how we would use the grid to show our working for multiplying by a single digit. And this can very easily be extended to multiplying by 2 or more digits. So let's have a look at a couple examples. 23 times 14. Well, there's 20 and 3. If you think about the left-hand edge here, we've got 10, 10, and 1, 2, 3. Along the top row here, we've got 10 and 4, making the 14 along. So 23 along this edge, 14 along this edge. And if we think about the total area of that grid, to complete that grid using the minimum number of Dean's blocks, we have a total of 322. So what we're doing is we're using the place values of each digit, and we're constructing this rectangular array. Using the grids, we have 23 and 14, 10 and 4. This time we've got 4 sections in the grid to complete. So 20 times 10 is 200. 20 times 4 is 80. 3 times 10 is 30. And 3 times 4 is 12. So the total inside the grid is 322. Now there are lots of different ways and lots of different conversations that can be had in terms of adding these numbers together. So for example, we could often talk about this diagonal. This diagonal is often helpful in terms of adding. So we could have 200, add the tens, so 200 add 110, then add the 12. But like I said, there are often lots of number combinations within these grids that are helpful to make the addition as easy and as straightforward as possible. So 52 times 83 would look something like this using the grid. 50 and 2, 80 and 3 would give the rows and the columns. 50 times 80 would be 400. So that's like 5 times 8 is 40 times 10 times another 10 to make the 4,000. 50 times 3 is 150. 80 times 2 is 160. And 2 times 3 is 6. We can add those together to make 4,360. A helpful way to add in this case might be to think about the 160 as 150 and 10. The 250s go together to make 300. Then you've got the 10 and the 6 making the 16. So it's nice to have conversations around good tactics to add the 4 numbers together. So pause the video at this stage and give this question a try. Okay, so using the grid, we have 20 and 3, 40 and 5, and we can start to populate that grid. So 20 times 40 is 800, 20 times 5 is 100, 40 times 3 is 120, and 3 times 5 is 15. And we have a total of 1,035. So 23 times 45 is 1,035. Now, one thing to say at this point is, let's take the 45, for example. Okay? Now, the initial impression here is that we're taking the 40 and the 5 because those are the tens and the units. And in many ways, that is the case. We can just take it from those digits. But we've also got to remember that these two numbers add to make 45. So let's say, for example, that your child isn't confident with the 4 times table, which plays a part in the 40. Well, we could think about how we could rewrite the 40. So the top of the grid, instead of having 2 columns, could have 3 columns. And it could look something like 30, 10, and 5. Still adds up to 45, but it's avoiding the use of the 4. So we could have the 20 along the edge, the 3 along the edge, and then inside the grid have 6 positions to answer. So be aware, although I've used simpler numbers there instead of the 40, in theory that could make the actual multiplications easier. But of course, instead of having 4 numbers to add up, we now have 6 numbers to add up. So there's pros and cons, but it is a really flexible approach. So maybe try out a different approach to answer either one of these questions on the screen, because you should get the same answer. So carrying this on to division, and what was previously known, and still is, known as long division. But the procedural approach that a number of us were taught is still visible when we use the grid. So let's take a bit of a historical look at division and trying to connect the learning. Okay, so 168 divided by 12 could and can and still is written like this. Okay, we have that, what seems to be known as the sort of bus stop way of writing it. Well, different contexts and eras have used different division layouts, commonly using sort of two lines, as you can see on the screen at the moment. But they all stem from an original layout, which is a rectangle. So that's very similar to this grid that we keep talking about. So let's make use of. So there on the screen I have the 168. I've got 100 square in the blue, 6 10 rods in the green, and then 8 units in the yellow. Essentially what we want to do is, we want to take the 168 and we want to create a grid. We want to create a rectangle using the 168. One of the measurements has to be 12. By setting it up like that, where we have used the 100 square and 2 of the 10 rods, and we have 12 along the edge, 12 boxes along the edge. So that is mirroring the actual formal written layout on the right hand side of the screen, where we've got 12 along this sort of left hand edge. The total inside has to be 168. So what we want to work out effectively is, how long is our rectangle going to be? Thinking about the traditional long division layout that you may be familiar with, if not able to kind of exactly remember how to do it, we've used up 120 of the 168, and you can see here we have 40 left over. So essentially what we're doing is we're subtracting these two numbers to get 48. So what we can start to do is we can start to work along the way. We want to keep that fixed height of 12. So I've got 10 and 2, 10 and 2, 10 and 2, another 10. So I've now used up all 48. Okay, having again subtracted these two to get that. I've now used up 48 and we get 0. Okay, so we have no remainder. Here, 168 divided by 12 is 14. So we've created that grid. We've created that rectangle, which is exactly what we want to do for multiplication and division. So one of the reasons, or one of the ways I should say, that we approach this in the classroom is, when it comes to dividing by a two-digit number, is it's as easy as 3, 2, 1. So let's take this example. I think I've got 2 or 3 in this tutorial for you. 156 divided by 12. Okay, so we've got this 3, 2, 1 idea that we're going to play with now. We know that we need to create a grid, a rectangle. The total of that rectangle needs to be 156. I need to be able to arrange my Dean's blocks, but we've moved on from that and we're now starting to show working in our jotters. So we've got this rectangle, it's 156 inside, and I know that it's got a fixed height of 12. So there's my 10 and 2. Okay, so we can start to construct our grid. So what I'm going to do is, I'm going to do a little bit of trial and error. I'm going to try 10 along the top here. I know that I'm going to get 120. If inside the grid has to have a total of 156, that means that the column total that's currently blank has to be 36. So, what number can I put in this top right position that will help me to do that? Well, that would be 3. 30 and 6 in those positions. 10 times 3 and 2 times 3. So 156 divided by 12 equals 13. And there is our 3, 2, 1. Now, we wouldn't necessarily expect the pupils to lay it out exactly like this, but the usefulness here is that you can actually see each step. When you do it all on one grid, it becomes a bit messy and you can't really work backwards and recall what each step did and how you came up with the final answer of 13. So laying it out like this in the initial stages anyway, we found really quite useful. So 208 divided by 16. Okay, so we have the total of 208 inside the grid, and we can start to construct the grid using the 16, 10 and 6. So I'm going to try 10 again at the top left position. 10 times 10 is 100 and 6 times 10 is 60. We have a running total of 160, which means that the total of the blank column would have to be 48. 160 add 48. So the next task really is to think about what number can go in the top right position to give us a total of 48. So that would be 3. 10 times 3 would be 30, and 6 times 3 would be 18. Now, depending on the class, it might be that we do quite a few of these on whiteboards first, because some pupils, may well not use a 3 there and use a 4, but they would quickly discover, of course, that we wouldn't get a total of 48 if we did that. So sometimes there can be an element of guess and check, which is absolutely fine. And using whiteboards allows us to do that really easily, just using the whiteboard pen and an eraser. So 208 divided by 16 is 13. And last one, 286 divided by 13, as easy as 3, 2, 1. So we've got 10 and 3 to make the 13, and we start to construct our grid. We can then put 10 in the top left position and start to work through the problem. So 10 times 10 is 100, 3 times 10 is 30. We have a running total of 130, which means the next column, the blank column, needs to have a total of 156. Now that's interesting because that's the first time that we've had the blank column needing to have a total that was bigger than the column that we've just made. So what we could do is have another column of exactly the same quantities, so another 10 and 130, and that means that we just add another column on. Our grid doesn't need to be a fixed size here, it just needs to make sure that we have an interior total of 286. So far we've got a running total of 260 from the two columns that we've got here, 260, which means that we have 26 to make the 286. So if we put 2 in that position, we've got 10 times 2 and 10 times 3, and we have a nice grid total of 286. So 286 divided by 13 equals 22. Remember, going back to earlier in the video, we're just looking at the totals here. you might want to pause the video now and try a few of these using that grid method approach and answers to those questions. What we want to have a look at now is the application of this method. Okay. I said earlier at the start of the video that the grid method extends into algebra. Now, those of you with a knowledge of, for example, National 5 maths, older children may be familiar with this method for expanding brackets, FOIL, and using these loops. Well, we don't use that now. What we do is the grid. So we pull it back to something like this, 23 times 14, which we did earlier in the video. 23 we can think about as 20 and 3, and 10 and 4 is our 14. So this here, albeit algebraic, is very similar. 20 add 3, 10 add 4. The grid. This time, the green doesn't mean 10. This time the green is x. So there is our x and our plus 3. There is our x and our plus 4. And we can start to populate that grid. If it was 10 times 10, it would be 100. This is x times x, which is an x squared. Then we've got x times and x times 4 to give us the green positions. And then we've got 4 times 3, which makes the 12. So again, we've got these patterns where we have the blue, the green in the diagonal bottom left to top right, and then the yellow in the bottom right. So that's consistent with previous learning, and it's familiar. That would be worked out by adding up each of those 4 sections within inside the grid, and we end up with an answer of x squared plus 7x plus 12. Now that's a bit of a whistle-stop tour of the algebra side of things, but it does allow us to connect lots of learning up in maths. Previously, this type of work would be seen as very distinct and not at all linked. But the algebra tiles and the grid method allows us to do that and build familiarity into the course. And we have noticed, even in our National 5 candidates this year, that there are a lot less mistakes being made with this type of work, which is fantastic. Here's how we would lay it out using the grid. We've got our x squared, our 3x, our 4x, and our 12. We would just simply add up the 4 expressions inside that grid. A further application is something called the lattice method. So let's take a fairly straightforward question, 43 times 6. The lattice method works a little bit like this. We don't use the place values, we use the digits themselves. So we wouldn't write 40 and 3, we just write the digits 4 and 3. The 6 is positioned on the right hand side, which again is different from the grid that we've talked about. We also introduced diagonals. So the tens digit goes in the sort of the top left box, and the units digit goes in the bottom right box. So for example, 4 times 6 would be 24, and 3 times 6 would be 8. And what we do with the lattice method is we look at those diagonals and we add those diagonals up. So 43 times 6 is 258. If you turn that lattice on its side, so the diagonals almost become vertical columns, That essentially is our hundreds, tens, and units. The lattice method is particularly useful when we're multiplying decimal numbers. It's a little bit of a novel approach, but it is a nice approach to extend pupils' knowledge and confidence of using different types of grid. But the one that's got the most longevity and the one that's used throughout our course is the straightforward grid that we have talked about. But this is particularly useful when it comes to decimal numbers. So 27 times 572 using the lattice method would be something like this. 7 times 2 is 14. 2 times 2 is 4. So you can see here that we don't have a tens digit, so you could leave it blank. We tend to encourage putting a 0 in that position. 7 times 7 is 49. 2 times 7 is 14. 7 times 5 is 35. And 2 times 5 is 10. We then look at each diagonal and add each diagonal up. You can see here 9 add 1 add 4 makes 14. So the tens digit, the 1, goes into the next diagonal, just as it would go into the next column. 5 add 4 add 4 add 0 add 1 in the green diagonal is 14. Purple diagonal total is 5, and then the blue diagonal is 1. So we could work around the L shape. 27 times 572 is 15,444. So you could pause the video at this stage, maybe try the grid method and the lattice method. You should get the same answer for both. Okay, so it should look like something like that. We've got 62, which we are writing down as 6 and 2 if we're using the lattice method. We're not using the place values. Then we've got 1, 2, 5 and 0. The whole of the bottom row there will be 0. 2 times 5 is 10. 6 times 5 is 30. 2 times 2 is 4. 6 times 2 is 12. And the top row, 2 times 1 is 2, 0, 2. 6 times 1 is 6, or 0, 6. We have those diagonals and we add up those diagonals. So the answer is 77,500. So that 0 there isn't necessary as part of our answer, it just drops off. So you can see here an example of some work comparing the lattice method on the left hand side with the most sort of traditional column sort of structure to the working. We are definitely encouraging the use of the grid because of its applications throughout the course. The lattice method itself is a bit of a novel way of doing it, but it works really well, particularly for decimal numbers. So there's the vertical sort of layout of this work. So that concludes this video on the grid method. There are some worksheets, there is a worksheet, sorry, with 5 sets of 5 questions to try a little bit of multiplication and a little bit of division. So enjoy.